All right, 44, 45, we're just listing possible rational zeros. That could definitely be an SAT question. You never know. Now, what's nice about having your the head of your polynomial, your leading coefficient. My dog is mad right now. He's mad when the kids start playing. When they start playing like rough, Obi like barks. Like I don't know if he's trying to like protect them or if he's just like, stop it, stop with your shenanigans. He just gets super protective. But we are looking for factors of 54, and we're going to have to go quite a bit of them. Let's see, 54 has obviously 1. It's even, so it's got 2. So 2 goes in there how many times? 27 times. So 2, 3 goes in there. 4, no. 5, no. 6, yes, because that's 6, and then 9. Okay. So then we need the 3. 3 goes in there 18 times, and then the 2 went in there 27, and then we got our 54. Okay. So that's good. We don't have to label all of these plus or minus because we took care of it just like that. All right, now this guy's a little different because we do have P's and Q's. So we need the Q's. The Q's are 1 and 3. Obi, chill. Okay, so the plus or minuses are kind of, they're technicalities because when you want to actually find the roots, you're going to have you have both of them. So 1, 2, 3, 4, this is 36, and then 6, 8, no, 9, yes, 10, no, 11, 12, 36, so then 4 times, 3 times 18, and then we got 36, and then we got everything. Now these are all the ones that are over 1. So now we got to put all these over 3. Okay, so P over Q. Now my kids are purposely trying to make my dog mad. Okay, so we got 1, 2, 3, 4. This is the answer. Okay, now let's put these over 3. 1 over 3, 2 over 3, 3 over 3 is 1, 4 over 3 is his own thing. 6 over 3 is 2, 9 over 3 is 3, 12 over 3 is 4, 18 over 3 is 6, and 36 over 3 is 12. So that's it. So you just had those extras. 1, 2, and 3, 1, 2, and 4 over 3s, those guys are the extras. Okay, so watch out for that. All right, we don't even have to test them. We were just supposed to list their possibilities. Now here, with the Descartes rule of signs, we want to give the possible number of positive and negative. So we don't actually have to simplify and find them like we do in the last 2. And I imagine these would probably be the longest problems of your test. But we can just see how they change signs. Okay. So remember how this works. We want to test for if we were to do this. Now we've done this before on our study guide, but we're going to do it here. But we're going to do it for the negative ones, but not the positive. The positive ones are very easy. You're looking for sign changes. And we do not see any sign changes. So, as far as zeros go, there are no positive zeros. So, if we had this long list, none of them should be positive that we test in synthetic division. All of them should be negative. Okay? Everything will be negative. So, how many possible negative ones are? Okay, well, let's take a look here. What we're going to do is we're going to change. I'm actually going to use a different colored pen here. And I'm going to write over the top what would be the actual sign. So this guy would actually become negative. He would become positive. This guy would become negative. He would become positive. This guy would become negative. And then he's positive. So we've got 1, 2, 3, 4, 5. We've got 5 sign changes. So this means we would have 5 possible negative roots. Okay, that's as many as we can have anyway. We could also have 3, or I don't need a comma there, or we could have 1. Okay, that's it. That's all it's asking. That's what Descartes' rule of signs does. And it can be pretty quick. Okay, it doesn't have to take forever there. All right, now the positive for this guy. We've got, nope, 1, 2. We got 2 or 0, right? Because we can always have just the even 2 less. Okay, it's either the most or less than that by 2. Okay, negative. So let's go ahead and change this. This guy would stay negative. This guy would become positive. This guy would stay positive. This guy would be negative. And then he's negative. So how many sign changes do we have? 1, 2. We only got 2 sign changes. So that would be 2 or 0. Okay. And there we go. Six minutes. Okay, now we're going to find all of the factors here for 48 and 49. Okay. So let's see what we can pull up. Oh, this is actually quadratic form. And I'm looking for factors of negative 48 that add up to 47, and that would be 48 negative 1. So this means I would have x plus 48 and then x minus 1. Okay, and then they have to be squared. Okay, and then we have to divide these guys by 4. Okay, so now we got x squared plus 12, and then this guy is x squared minus 1/4. So what that usually does is, because of the 4 here, we can actually do this. Okay. All right, 4x squared is, because if you remember the new AC method that we did, we can put the 4 right here, because what we want to do is we want to solve for these guys set them equal to 0. Okay. Now this guy, even if you left it here, what's kind of cool is that you could have factored this guy 2x plus 1 and 2x minus 1. But let's say that you left it like this. What would have happened is you would have had x plus 1/2 and x minus 1/2. Now this spells out your answer anyway. This is going to give you negative 1/2. This would give you positive 1/2. So you've already got, these guys are the same thing. Okay, it's just we're used to writing, putting a number there. We're not used to having a fraction here as part of our factoring. But that's good. So it looks like our zeros, we actually already have 1/2 and negative 1/2. Okay, now let's see what we get over here. Now over here, we've got to set x squared plus 12 equal to 0. So x squared, we're going to move that 12 over to the other side, because this is taking the square root method of solving a quadratic. Because we don't have a middle term, we don't have to do any other factoring, and it's definitely not the difference in 2 squared. So now let's take the square root, and we'll notice that we're going to get the square root of negative 12. Okay, and there's also a pair of 2's in there, so we would have plus or minus 2i square root of 3. So we've got 2i radical 3 and negative 2i radical 3. And those are our 4 zeros, x to the 4th. So 1, 2, 3, 4. So we actually covered the non-real solutions. We didn't work with those very well, or very much. So if this is a little strange, I can see why. These guys just are not, we haven't played with imaginary roots yet. Okay. All right, now this guy's going to be a little different. He's a cubic, and in this case, oh man, we got factors of 60. No, because 9, I'm not going to be able to use grouping or either. I am stuck using the rational root theorem here. And what I need to do is basically just list all my possibilities. And there are a lot. I mean, we're talking, you got 1, 2, 3, 4, 5, 6 is even in there. You got 10, 12, etc., etc. I got a lot of them. So what I'm going to do is I'm just going to start with 1, -1, then 2, -2. And what would happen is as soon as I got to +2, I would have actually got a root. So let's see what happens. So you would have got 3 deep there. That's why it doesn't make sense to list them all here unless they're asking you for the list. You don't have to list them all. Just start off with the list and just know that it'll probably be within the first 6, okay, usually. But we're going to go 1, 9, 8, and then -60. 1, 2, 11, 22 is 30. That's +60. And so we go, 0. So it looks like we have our first batch of factoring is x minus 2, okay? And then we've got x squared plus 11x plus 30. Okay, now what we're trying to do, though, is we are trying to find the zeros, and even complex zeros, irrational zeros, whatever. We're trying to find them all, okay? Now, in this case, though, this is going to work out nicely because this is actually factorable. Factors of 30 that add up to 11 are 6 and 5, so this is actually really nice. X plus 6 and then x plus 5. Now, to find the zeros, you just set that factor form equal to 0, and you will find that your zeros are 2, -5, and -6. I don't know why I switched the order. It doesn't matter. Okay, but there we go. That's it. That's the game. Good luck, everybody.